Alright, in this slideshow here we're going to talk about bridging, switching, and collision domains. The need for switching. This is kind of the reason why hubs are becoming obsolete. When the number of devices trying to access the network is low, the number of collisions stays well within the acceptable range. If I have, just 5-10 computers plugged into a hub, which would be one big collision domain, the number of collisions is going to be relatively small, and that's acceptable. But the more computers you add to that hub, the more collisions are going to happen and the more detrimental it's going to be to your network. So for this reason, bridging was developed, helped ease the performance problems that arose from increased collisions. And then from bridging came switching. A bridge is basically just a two-port type of switch. Switches are multi-port bridges. A bridge keeps a table of MAC addresses and the associated ports, and I'll show you an example of that here in just a little bit. The bridge then forwards or discards frames based on the table entries. So here in the middle we have a bridge, and it has the two ports, one going up to this top segment and one going down to this bottom segment. With here we would have two collision domains. Now we'd have one up top and one down on the bottom. The more collision domains, the better. Because what happens in a collision domain is if they detect a collision, all the computers in that domain must stop transmitting, wait for that collision to be detected, and then they can go ahead and retransmit again. So there's only two computers on each collision domain, which is a good thing here. So the bridge has just started, so the bridging table is empty. The bridge just waits for traffic on the segment. What happens is host A is going to ping host B. So since the data is transmitted on the entire collision domain segment, both the bridge and host B process the packet. The bridge adds the source address of the frame to its bridging table. It knows it came from A, and A's MAC address is that 00000C with a bunch of A's, and that's on port 1. The destination address of the frame is checked against the bridging table. The address is not in the table yet, so therefore the frame is forwarded to the other segment. The address of host B has not been recorded yet. So look in the bridging table for the destination of host B. Host B was not in that MAC address table, so what it did is it flooded it out port 2, trying to make it to host B. Host B processes the ping request and transmits a ping reply back to host A. The data is transmitted over the whole collision domain again, host A and the bridge. The bridge adds the frame source address to its table now because it knows it came from host B, so it puts host B's MAC address into the table and associates it with port 1. So as the destination address is already in the table, it's associated with port 1, the frame is not forwarded out port 2. So let's review what happened again. Host A tried to ping host B. When that ping came to the hub, what the hub does is it will flood it out every port. So that ping comes out and goes to the bridge. The bridge takes a look at that ping, sees that it's destined for host B. It will look in the table to see if host B was in the table. It was not at that point in time. So what it did is it flooded it out its second port to the other computers. Also, that hub would have flooded it over to host B. Host B would get it, accept it because it's for him, and now he sends his reply back. When he sends his reply back, the reply gets to the hub floods it out the ports. The bridge would get it, look at it, and see that the reply was destined for host A. Host A is in the MAC address table, so it would stop it right here at the bridge. It would not forward it on because it knows that host A is on port 1. So that message would then be received on host A, the reply back, and he would accept it. Host A pings host C now. Host B receives but discards the frame since it was not intended for the destination. The bridge would then just renew the source address of the frame to its bridge table. Host A is already in there, so it's coming from. It's already in the MAC MAC address table, we'll just renew it. It did not know where host C is, so what it would do again is flood it out the ports. So since the address is not in the table, the frame is forwarded on to the other segment. The address of host C has not yet been recorded. Host C processes a request and is going to do a reply back. Now when that bridge gets the reply back, it knows it's coming from host C and that host C is on port 2. So it puts host C in the MAC address table and associates it with port 2. Last thing we have going on here is host D pings host C. The bridge adds the source address to the bridge table because it's coming from D, so we'll put D in that MAC address table. We're trying to get over to C, so what happens is the bridge looks in the MAC address table for host C. It sees that the host is on port 2, so it does not need to send that traffic on through port 1. It would just stop that traffic right there. So bridges make decisions based on our MAC addresses, or also sometimes called layer 2 addresses. Bridges create collision domains which reduce traffic but do not affect logical or layer 3 addresses. They're only dealing here with our MAC addresses. MAC addresses are talked about in the reading with the Cisco stuff, so you might want to take a look at that. The entire network will be part of the same broadcast domains. If you take a look at this picture down here, we would have 2 collision domains with our dotted line with segment 1 and segment 2, but one big broadcast domain. If you remember what a broadcast is, the broadcast is trying to send out to every single computer. So if computer 123 wanted to send to every single computer, it would send out a broadcast. And bridges do forward that broadcast, so that message would come down to the hub. That hub would forward it out all of its ports, so 124 would get it, 125 would get it, the bridge would get it. The bridge would then see it's a broadcast, so he would forward it out, the hub would get it, 126 would get it, 127 would get it, and 128 would get it, because it's a broadcast. It's all in one big broadcast domain. They all would take a look at it. The only thing that can break up a broadcast domain is a router. So like I said, a switch is basically a multi-port bridge. Each port on a switch is going to be its own collision domain. So a 20-port switch would have 20 collision domains. 8-port switch, 8 collision domains. Increasing the number of collision domains is known as microsegmentation. This is a good thing. We want the more collision domains, the better. A switch builds a CAM table, or a content addressable memory table, which basically is like a MAC table of a bridge. The switch dynamically builds and maintains that CAM table, holding all the necessary MAC information for each port using ASICs. I don't expect you to know what ASICs are, but I want you to know that when a computer is sending information, that switch would then store the MAC address and the port that it's associated with, just like the bridge did in that previous example. So if host A is sending to host B, and host A is on port 32 of that switch, it would associate its MAC address with port 32, so it knows where everything is going to be at on that switch. Full duplex is what we ultimately want to get. With a hub, we cannot achieve full duplex. To do full duplex, we must have our network card and a switch. In full duplex, there's going to be no contention for the media, so there aren't going to be any collisions. With full duplex, we're theoretically doubling our bandwidth because we can send and we can receive at the same time. So if I can send at 100 megabits per second and receive at 100 megabits per second, we're theoretically getting our 200 megabits per second of throughput. Again, remember there's a little bit of overhead and some things that can decrease that speed, but theoretically that's what we can get. So switch benefits: enables dedicated access, eliminates collisions, and increases capacity, and supports multiple conversations at one time. So in this example here, we have one big broadcast domain again, but each port on this switch is going to be a collision domain. So we have one collision domain, 2, 3, 4, 5. And now what happens when the server wants to communicate with the top PC on the upper right here, that message would just come down to the switch and right over to the computer because it knows where everything is located. If this were a hub, with a hub we'd have one large collision domain. And what would happen if this server wanted to send over to the upper right PC is the message would come down to the hub, and when a hub gets a message it floods it out every single port. Very inefficient because these computers do not need that message. It's not intended for them. So with a switch we are making our network a lot more efficient. So if you ever want to get a nice increase of speed and reliability on your network, replace all those old hubs with some switches. Latency is talked about in much more detail in the timing and things in the Cisco reading, but this is all I'm going to mention about it. Latency is the delay between the time a frame first leaves the source to the time it gets to the destination. Now, some things that can cause latency or delay are the media, electronic processing of that signal, software switching decisions, and the content of the frame. There's some different type of switch modes. I don't expect you to know this for the test, but if you've ever taken a look at a switch to purchase them, you may see these switch modes. And so I kind of feel it's important that you know what it's talking about. With switches, time is of the issue. Users want their computers to work as fast as possible. How a frame is switched to the destination port is a trade-off between latency and reliability. A switch has 3 different methods it can use in processing the frame. Here are 2 of those methods. First one here, cut-through switching. A switch can start to transfer the frame as soon as the destination MAC address is received. This is the lowest latency, but there's not going to be any error correcting. So as soon as that switch gets the frame, just forward it on to the correct destination. Don't check for any errors. Store and forward. A switch can receive the entire frame before sending it out to destination port. This gives the switch software an opportunity to verify the FCS with the frame check sequence. So with this we're going to be a little bit slower, but we're going to check that entire frame for any errors before we send it off. This must be used for asynchronous type of switching. We have symmetric type of switching and asymmetric. And again, with the asymmetric, you need to use that store and forward. With symmetric, the source and destination ports have the same speed, and that frame is kept intact. For asymmetric, we have different types of speed. And here's what I mean by that. This is symmetric. So if the server wanted to communicate with the PC on the bottom, and they're both 100 megabits per second, we just know right away that we can send back and forth. We don't need to store, switch to a different speed, and then send. What happens before 2 computers are going to communicate, they'll send some information back and forth to determine what speed they are and what speed we can send at. We always must send at the slowest speed. So for example here, the server has 1000 megabit connection to the switch, and that source has 100 megabit connection to the switch. So we're 2 different speeds here. So what these 2 computers would do is before they communicate, they would send some information to realize that they only can send at 100 megabits per second. That's their max. So what would happen is when we send that information back and forth, we'd have to store it from one speed and then slow it down and send it to the source out that slower speed. So that's asymmetric type of switching, just different speeds. The last type is called fragment free. It's kind of a compromise. The first 64 bytes are going to be read, and then it's going to go ahead and send. This slide here kind of shows all the different switch modes. So with the store and forward, we would take that complete frame, check it, process it, and then send it. With the cut through, we just take the first part of it as soon as we get the destination address and then send it. No error checking again, lowest latency. This is usually the default type of mode for most switches. And then we had that compromise, which would do almost the whole type of process, almost the whole frame, but not quite. This will filter most errors, but doesn't get everything because it's not recalculating that FCS. Alright, collision domains and broadcast domains here. It's important to be able to identify a shared media environment because collisions only occur in a shared type of media environment. Here's an example of shared media environment. This would be like a bus type of topology. You're not going to really see this anymore, but you'd have one big cable. Each one of these computers would be plugged into that cable or vampire tapped into that cable, and you would actually share that media. What you probably would see for a shared type of media is an extended type of media. This middle piece here could either be a repeater or a hub. What a repeater does is just regenerates the signal so it can go longer distances. The limit for Ethernet is 100 meters long. If I want to extend past 100 meters, I'd have to implement a repeater. And then point-to-point would also be a shared type of media. Collision domains are the connected physical network segments where collisions can occur. Collisions cause network inefficiencies. So what we want to do is we want to break up collision domains into more domains. Here's a reason why we want to break up those domains, and also to implement switches instead of hubs. This is the 5-4-3-2-1 repeater or hub rule. Basically, a repeater is a 2-port hub. We want 5 segments of network media, and of those 5 segments, only 4 of them can have repeaters or hubs. 3 of those can only have hosts on the segment, 2 link sections then with no hosts, and 1 large collision domain. And I'll show you an example of what the 4 repeater looks like here. 4 repeater rule looks like here in just a minute. What a collision is when 2 bits are propagated at the same time on the same network, a collision will occur. Basically, they're trying to send information at the same time, so those bits will collide on the cable or on your network, and they will cause what's called a collision. They're not inherently bad. They're just a normal function of legacy Ethernet, but we can take care of these and get rid of them by, like I said, replacing that hub with a switch. Networks with only layer 1 components are a single collision domain. So hubs and repeaters are layer 1. They are all going to be a type of collision domain. So again here, shared access, extended by a repeater, extended by a hub. These are all one single collision domain. So in this example down here, the extended by a repeater, if the first 2 computers wanted to communicate and they communicated at the same time, a collision would happen. And that collision then would have to be propagated to every single computer, printer, hub in that collision domain, causing some latency, some delay in our network. How many collision domains would we have in this setup? We would have 1 big collision domain. These are all hubs in here, all layer 1 devices. I'll show you an example of how collisions work with Packet Tracer here at the end of the slides. How would you solve this problem? You could add a bridge, and if you added a bridge, we would now have 2 collision domains. That would help a little bit. What would help even better is if we took all these hubs, replaced them with switches, and then we would have however many ports we had on a switch. That's how many collision domains we would have. So 2 collision domains with that bridge. So segmentation, how do we break up our collision domains? Well, layer 2 devices break up or divide collision domains. Segmentation makes networks more efficient and allow data to be transmitted on different segments of the LAN at the same time without the frames colliding. So for example, here we have 4 different segments, 4 different collision domains. Here we would have 6 different segments, 6 different collision domains. We can also segment with routers. So bridges, switches, and routers will break up our collision domains. This here is talking about layer 2 broadcasts. It does talk about these in the slides, in the Cisco reading. I'm not going to go through this in a whole lot of detail, but basically what I want you to know about layer 2 broadcasts is they are going to be forwarded by our switches, by our bridges, by our hubs, and our repeaters. The only thing that will break up broadcasts from being forwarded our routers. So in this one here, if we had our switch in the middle like we do right now, we would have two collision domains, but we still have one big broadcast domain because this would forward it. With a bridge, same type of thing. One big broadcast domain, two collision domains. If I threw this router in here, the circle one, the router would break up that broadcast domain. So if one of these computers wanted to send a broadcast, the broadcast would get stopped at that router. So in this example here, with the bridge in here, we have two collision domains, but we have one big broadcast domain. If we took that bridge out and we put in a router instead, we would have two collision domains and two broadcast domains. That is incorrect there. That would be two broadcast domains, one on this side and one on the other side. So a little type of summary here. Bridges and switches are layer 2 devices. They forward frames after examining the destination MAC address. They look in their table. If it's in the table, forward it right to the destination. If not, then we'll flood it out with all the ports until we finally get that destination into our table. Each port on a switch has a separate collision domain. Small collision domains equal less collisions. The STP we did not talk about. All the rest of these slides you can kind of use to quiz yourself. This is available on the bsconline.org site. It's under the heading switching. So if you want, you can go through and quiz yourself with all of these. I'm just going to go through them real quick here. This is what I want to take a look at here. How many collision domains would we have in this particular example? Well, again, every single port on a switch is a collision domain. So I'd have one collision domain, two collision domains, 3, 4. Router also breaks them up. So here I would have 5 for the top port of the bridge, and then 6 for the bottom port of the bridge. So I'd have 6 collision domains. How many broadcast domains would I have? I would have 2. One on the left side of this router and one on the right side of this router, because a router is the only thing that can break up a broadcast domain. So I have 2. Another example here. How many collision domains would I have? Let's see if we can figure this one out. Every single port on a switch, so 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 10. Here would be 11. This would be 12. 13, 14, 15, 14. They must just count this top one here in between here as 1. So 14. So again, here they are again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 for the top port of the bridge, and 14 for the bottom port of the bridge. How many broadcast domains are there? There's going to be 4. One for every port of that router. Alright, what I'm going to try to do here is show you how hubs and switches and collisions work. This is on Packet Tracer version 3.2. This is the old version of Packet Tracer. If you want to download and install it, you'll have to do a Google search for it. I think it was the first hit when I did a search for Packet Tracer 3.2. There was a download link for it. Or you can set up a similar type example with the new Packet Tracer 4.11 if you want to play around with it a little bit. I'm using the old one here because they already have some set up. that are pretty easy to use. So I'm just going to come in here and do this hub repeater hub one. This is what our network looks like, and I'm going to send some pings. They're going to cause some collisions here. Ping PC6 and PC5 are going to try to communicate at the same time, and they're going to cause a collision. So they send, a collision happens. Every single computer needs to know about that collision. So they all have to stop transmitting while they learn about that collision. Now they're able to send. When the hub gets a packet, what he does is he floods it out to all of the ports. Okay. Collision happens. Every computer must know about that collision. Very detrimental to our network speeds. Okay, show you how a switch works here. With a switch, when we want to send information, the packet will go up to the switch and then just go directly to the PC that it needs to go to. Goes right to the switch, directly to the PC that it needs to go to. Whereas that was a hub, it would flood it to every single port. A couple more examples here. It's not the one. There we go. Rather large, only one big huge collision domain on here. This link is just down here, so save us a little bit of collision time, but computers are going to send pings, collides. Now every single computer has to know about that collision. Now that ping comes back. See, the bad thing about hubs and repeaters on here is they just flood the traffic out. Hub gets it, send it out to every single port, even if it's not destined for those computers. Access point, a wireless access point is basically like a wired hub. So how I could make this better is if I took out this repeater, and let's throw a bridge in here. Oops. Turn it on. Connect them. I used the wrong kind of cable here. I want to use a crossover because they're like devices. Also, I'm going to take this hub out of here. Take that one out and we'll put in a switch. connect all these real quick. Got it all cabled out now with a switch and a bridge, and we'll see how this looks a little bit different than it did last time. Now that collision happens. And we'll see here that that bridge stops that collision from being propagated over to the right side. Another thing to take note of here is that the switch down here stops that blue packet from being sent further, because it's not destined for any of the PCs down here, so why send it? One more quick example. This one's just for fun here. This would definitely violate the 54321 hub repeater rule. Bump to hubs, collision happens, and it's got to be propagated out through that whole network.